Okay. So I just want to ask project questions. Anyone have any questions about the project? And you can turn your mic on and speak if that's easier. Okay, no questions. Whoa,
Are
whoa.
there
There we go. My volume
are
is
there
very
any
loud.
limits?
Limits on what?
Are there any limits to the sort of messages that we can send in between processes? Like before, we couldn't send certain information.
I mean, I want you to follow the algorithm, right? So the algorithm tells you what you should send. So you should send a proposal. Now, this is for a regular. So recovery, you do you. Whatever you want for the recovery, you can use whatever you want. I don't care. But when you're sending the messages in terms of the synod algorithm, um, you should include the proposal. So that includes all the information for updating the log and the data structures, the type of message, the sender ID, things that are naturally included on a message. But I don't want you to like invent your own algorithm on top of a synod algorithm. So does that answer your question?
Yeah, thank you.
Okay, great. All right, let's see. My chat window is too tiny. Let's make it bigger. Uh, Okay, so proposal numbers. If a site one always starts with proposal number one and does 11, 111, etc., you make three consecutive proposals. Do you always start with proposal number one, or does each subsequent call of the synod algorithm use the current max proposal number? So it depends whether you're doing the same log slot or a different log slot. So that's why like kind of the log slot that you're proposing for should be part of your proposal, right? So remember there's one instance of the synod algorithm per log slot. So if a proposer is trying for the second time on the same log slot that it did the first time, then it will increment its proposal number. Because a reason that it could have failed was because its proposal number was too small, but also because when you get back messages, so I mean, if you won't probably experience this. I mean, you shouldn't have to necessarily code for this, but in practice, like you might get, if your timeout is too small, you might get a response to proposal one after you sent, prepare 11, right? And so you want to make sure that you know like what you're getting the response to. So kind of changing the proposal number in between like retries is important for the single log slot. But then once you go to the next log slot, you start over again because every proposal number is valid for a particular log slot, and then you can reuse proposal numbers when you go to another log slot. Does that clear that one up? I see kind of like the follow-up. Maybe I'll just do that and I'll go back. So when a proposer gets a NAC, do we automatically increment our proposal number until it's greater than the max num, or should we only increment the proposal number once between every synod algorithm failure? With the chance to fail recovery more than once until our proposal number catches up to max num. Okay, so the question about, so the max num is sort of saying, like, if you don't hear anything as the proposer, you're going to do one, and you're on the same log slot, you're going to do one, you're going to do 11, you're going to do 111, and then you're going to stop. If you hear back, so you say you send proposal one, and you hear back a NAC, you send a prepare, and you hear back a NAC with 12, then you don't try again with 11, right? That would be silly because you're going to fail, right? So in that case, you skip over the 11 and you go to the 111. Okay? So the NAC is there to help sites make progress. So you should use the information on the NAC to increment the proposal number. Yeah, so each time you start using a new log slot, you start at proposal number 11, you keep incrementing in a reasonable way so as to try to win the log slot. Okay, now let me go back before I lose track of things. All right, for pledging, is it all right if when I try to pledge, I always increment the pledge counter even if the pledge is not accepted? Yeah, that's fine. That's not something I'm really testing you on. So since we're not auto grading, that's okay. Okay. When the proposer gets an act, do we automatically? Yeah, okay, I answered that one. for the recovery, say we have 3 consecutive holes and failed to fill in for the first hole, do we stop recovery? Do we try to fill in the other 2 holes as well? You stop. Right there, you stop. Well, okay, let me just say, your recovery algorithm is whatever you want, right? So that's not true. Like you do what you want. You should stop after some amount of time, right? Don't do less than 3, but if you want to do something different and not even try this in an algorithm, like that's your call. It should have a termination guarantee. Like recovery must terminate. Now remember, recovery can't be guaranteed to recover everything because impossibility of consensus, right? So you just got to do your best, and at some point you just have to declare that was my best and I'm done. And please don't make it take forever because like I need to grade this. So termination is key here. And then in your project report, you're going to explain, what your procedure was and why it terminates and possibly that it could terminate in these failure cases that you're bringing up. So these are really good things to be aware of, and just say how you deal with them. But you can't not deal with them, right? Even if you fill in all the holes and now you're like just doing the end of the log and you're filling in your end of the log, like those proposals could still be being created while you're filling in your log. So like you could be playing catch up forever. So eventually you just have to declare it done. There's no way to have reached complete recovery, right? Like that's impossible. So you just have to do it as best you can. I mean, not as best, but like what your algorithm says, what you feel is sufficient, and then that's it. Okay. All right, so that's that. Okay, now we go to the next one. The site has to make a proposal. It checks for holes in its log and tries to fill the holes. If the filling in the holes fails for some reason, we should just print out a failure, right? Yes. So exactly, you don't have to do anything else. Just say, I mean, the same failure error message that for any other reason that the proposal fails, like could not create project or whatever it says in the spec. Now remember, in standard error, I want you to print your message like sending and receiving, so that I'm going to be able to look at this back and forth and understand like why you're getting an error message, right? So please make your debug messages meaningful and not overly crowded. I just want to see the messages, not every kind of if statement check and formatting check and everything. I want your standard errors for me to grade off of, so please keep that in mind. Okay. Can Max and Ax send the proposal number for which they were fired beside? Yes. So the Max and Ax, any message that you're sending between proposers, learners, acceptors should be, other than recovery, you do whatever you want, but other than recovery, but those are always associated with a log slot. So you can send the log slot, the proposal number, I'm not sure for which they were fired. I guess I don't quite understand. Okay, can you clarify what do you mean by that? Okay. Okay, while you're writing, I'll handle the next one. Are we required to send NACs back to proposers, or is that part of the algorithm and optimal optimization? Please send the NACs. I mean, it is an optimization in terms of correctness, but if you were ever going to go out into the world and implement Paxos, like you would do this, right? Because the idea, even though this is an asynchronous system, we want to optimize for latency. And so sending the NACs is a way to make sure that we don't just rely on timeouts to just make a decision. So please send the NACs. Is there an upper bound on the log size for the assignment? If your recovery algorithm is just send the logs around. What would be an upper bound? I mean, I guess just I can't really tell you log size, right? Because that's kind of up to your particular encoding and how you serialize things and how you store things. But what did I say? 20 log entries was the max for the project 2, so we can rely on the same thing for project 3. Yes, I can't believe each log slot has its own max proposal number. Yeah, This is why I have you implement this, and it's not because, and I wish that the threading and the sockets weren't such a struggle. Um, I will try to maybe adjust for that later, but like implementing this algorithm makes you understand what all the pieces are for, right? I mean, I could do this on paper and you could look at it and be like, yeah, that makes sense. But everything in Paxos is written the way it is for a reason, and it's really helpful to implement it to understand that. Okay. The way I implemented messages handling lets old messages accumulate in a queue. This means that a NAC from a prior execution of the synod algorithm could stay in the queue for too long, even when the proposal number has been implemented. Yes, yeah. Oh, okay, no, I understand what you're saying. Yeah, so you can, when you send a message, yeah, you should say like, this is in response to proposal number one. This one is in response to proposal number two. Yes, definitely that should be in the message. Is that what your question was? Yes, yeah, you definitely want to be able to associate. I mean, the message pattern of Synod is a request response, right? So the proposer sends a request, the acceptors send a response. But because we're in this asynchronous system and we don't necessarily have any guarantees on message ordering, you need to pair up a request, and a response, and you can do that through the proposal number. Do you have to manually verify a distinguished proposer is valid, or can we assume the rest of our system is set up so that it only ever be designated to one sender? That's a deep question. I will tell you that the system, if you follow the spec in the project, is set up so that there will only ever be one designated sender. So, what the algorithm that I told you to use to pick this distinguished proposer is correct. So we will guarantee that there is only one. But I did say that each site should verify that when it gets that special proposal number 0, you don't need to send messages to verify, but a site can check, like, are you the distinguished proposer? A site knows when it hears that proposal number 0, it knows who that should be, because it can look at the previous log entry and see who the winner was. And if that site doesn't know who the winner was of the previous log entry, then it can ignore that and say, like, no, you're not valid to me. I don't know who you are. And it'll just make it do the full Paxos Synod algorithm instead. And so just an aside, because someone asked this in office hours this week too, is that this optimization, this distinguished proposer optimization, is not something that I invented. This is something that's used in a Google product called Megastore, which was a Google, like a geo-distributed database, and they use it for replication. And so this particular optimization is meant for situations where you have kind of what we call like bursty load, so that you have a site that's going to make a bunch of proposals in a row, right? So it's going to do a bunch of updates to the database, that client, and then that client's going to go quiet for a while. And then some other site on some other continent is going to make some updates to the database. And so if you have this kind of workload where you have a site making a bunch of proposals in a row, then this optimization is useful, right? It gives the distinguished proposal role to a site that is most likely to make the next command, issue the next command. And so the point here in Paxos in these optimizations is try to reduce the number of message rounds. And so this is a way to get rid of 2 message rounds in this case. And if we had used like external leader election as specified in the regular Paxos algorithm, then the leader would always be on one continent, while potentially, the workloads are spread over a bunch of continents. And so even though you could get rid of that one message round, you'd still have to pay the price of those sites forwarding their proposals to the distinguished proposer. So it could propose, so you'd still pay that kind of like cross ocean or cross globe message latency to get the proposal to the distinguished proposer. So by using an optimization like this, that if you have a workload that is bursty, then it naturally puts the leader where the next proposal is going to be. Should recovery algorithm messages be included in standard error? That would be helpful, yes. I'm going to read your report for understanding your recovery algorithm, but it is always nice to see some evidence that your report and your code are doing the same thing. If I'm suspicious, I open your code, but generally it's pretty easy to tell from like quality of a report and the quality of the output of a project what's going on. So I got a private message. I won't read it now, but I'll tell the sender that you're not the first person to request this, and yeah, well, I think we're a little more advanced. I'd like to think that, but I will keep it in mind. Okay, other questions? All right. Well, hopefully we'll have time at the end of class. Now, there's not a lot of submissions in Submiti yet. Maybe that's not a problem because the test cases are just really, a formality almost, not. So maybe you're all working on it already, and or maybe this is not that hard. I hope that's the case, but I am a little concerned. So please reach out if you need help, personal or otherwise, that's preventing you from doing this project. Do it today. Don't wait till Sunday, 10 p.m. when I can't do anything. So please, if you need help, contact me, okay? Okay. Extension. Well, nobody has reached out for any help. So, you got to tell me what's going on and why this is necessary. And I totally, please don't do it in the chat. Like, please contact me over email. But, I have no information. I can't take any action. So if you feel there is information I should have, please send me an email. Okay. All right. So then the next thing we wanted to do was talk about the two practice questions that I put up on the Submiti course materials page. So hopefully this is going to work. Yeah, so I'm seeing a concern in private message said, please email me about this. This is not a new phenomenon, and I imagine it's worse right now. So please email me. This is something I know how to deal with. Okay. All right. Let me share the web. So you can see my super advanced Microsoft Edge now, hopefully. And video. You guys over to the other monitor. All right. Okay. So can you see the browser window? Yes. Thanks. Okay. Got myself set. It's always like one click away from completely just crashing, I feel. Okay. All right. So I know I said I'd go over these, so I don't know. Hopefully you've taken a look. If not, you don't want to hear the answer, just turn off your sound for a few minutes. So these are two questions that come from past quizzes on FLP, so I could give you a sense, because I do understand it's like, what on earth are you going to ask about a proof, a really long proof, right? So the first one was about particular lemma 3, which is the long one, right? And we had this kind of set C hat and this set D hat and this kind of special event E that would take us from one to the other in terms of configurations. And the question was, why does this lemma only make sense in the context of an asynchronous system? If we had a synchronous system, not this lemma, but the proof, like what would fall apart in the proof? And there's a couple of things, but did anyone want to guess at one? Did anyone look at these questions? Okay, so given that probably you haven't looked, which is fine, because I don't expect you to start studying way in advance. Do you want me to tell you the answers, or do you guys want to have these as practice that you can do on your own? Just give me your opinion privately, publicly. All right. Have you like turned on the movies in the background here? I got one answer. All right, 1 vote for give you the answers. 2 votes for answers. I should have set up a poll. All right, 3 votes for answers. Okay, it's a quorum. Give you the answers. All right, so I mean, I think the second one we can talk about maybe more casually. The first one is going to involve remembering what the proof is, and yeah. Yes. If you don't want, I'll just mute, and when I close the browser window, that's when you know we're done. So the first one involves remembering how the proof works, and I totally understand if you haven't looked at the proof, you have no idea how the proof works, right? So this one is probably more just me giving you the answer. So if you remember, in the proof, we had this, it's a little bigger, we had this set, this configuration C, and then we said there's an event, right? So E, and I can write with this, right? No? I thought I could edit on here, not on this. Okay, well, I'll just have to talk then. E is an event that you can apply to configuration C, right? This little E. And then if you remember, the first thing in this proof was a note that said that if you can apply this event E to configuration C, then you can apply this event E to any configuration inside the set C hat. And the reason you can do that is because, anyone remember why? No? Okay, so we have this configuration C, and then we apply a bunch of, some schedule, and we end up in C hat. But what's special about that schedule is there's no event E in that schedule, no little event E, right? And then we apply that little event E, and we go into D hat, right? So we start in C, a bunch of stuff happens, we're in C hat, we apply little E, and we end up in D hat. And the claim in the beginning was that we could apply that little event E to any configuration in C hat, right? And that is only true in an asynchronous system, because if we're in a synchronous system, we said, okay, we're in configuration C, and then event E is applicable, then there would be some time, E is, remember, is a message, there would be some time at which that message would be delivered, right? And then after that, E would no longer be applicable, right? The synchronous system says that after some amount of time, then E's got to happen. And that configuration set C hat is, it's not bounded by time, right? So we can't expect that anything that's reachable from C can also have E applied, because E can only be delayed so long in a synchronous system, and then E has to happen. So that claim about being able to apply little E to everything in C hat, that wouldn't hold in a synchronous system. Okay? That answer that question? Questions about that answer? Still not clear. Okay, let me switch over. Right, so I'm just going to switch over so I can write on something here. Okay. So if you remember, we had our configuration C, right? And then we had this set C hat, and then we had the set D hat, right? And you could do a bunch of stuff to get into C, so that was some signal. Oh, I lost my chat, sorry, just a second. So clunky. I have to do this next semester. I have to get some better setup. Okay. There, now I can see. Okay, so we had some set of configuration C hat that we get to by events happening that don't include little e. And then we have little e happens, and we end up in a configuration inside D hat, right? And the first part of lemma 3, we're saying, so this was bivalent, right? And that was the whole idea, is that there's, some bivalent configuration in here. And so this is saying that the first step in the lemma was saying, like, no, like if you can apply E could be applied here, right? And therefore we can conclude that E can also be applied anywhere in here. But that's not valid if the system model is synchronous, because E is the receipt of a message, right? And in the synchronous system, you know that's going to happen in a certain time period. But we know that there's no time period limitation on sigma, right? It's any configuration that's reachable from C. So there is some schedule that's longer than the time period that we could wait for E to be delivered. Therefore, we can't assume that every configuration inside C hat will also have the ability to apply E, right? That, like, my algorithm doesn't have to be written so it expects E to come in at any time in the possible future. My algorithm has to be written to expect E to come within a certain time window. In order to satisfy this kind of chain of events here, we would need our algorithm to be written to expect E at any time in the future. And that's just not, you don't need to do that in a synchronous system. So I don't need to make that claim about my algorithm. Does that clear that up? Would that mean that some events in C hat wouldn't be in the set in a synchronous system? No. Well, I mean, there's lots of ways to kind of break a proof, but what they're saying is that anything in C hat is something that's reachable from C, meaning there's some schedule that can get me there. It doesn't matter how long the schedule is, right? So maybe I could change the proof and say, okay, well, if I wanted to be able to apply C to any apply little e to anything in C hat, then I have to put a restriction on sigma. That would be another way to say, like, the proof is broken. I think we're, like, saying the same point. We're just saying different ways to fix it or adjust it. It can't be fixed, but adjust it. Okay? All right. Any other questions about that one? All right, well, maybe I'll stay over here because I know what the other question is. So the next question was about, so if you remember at the end when I talked about leader election and the kind of the implications of FLP was that, I'm sorry, I told whoever I told that I'd close the browser window when I'm done. I'm not done. This is question 2. So practice problem 2. So that since FLP says it's impossible to solve the consensus problem, as a result, it's also impossible to solve the leader election problem. And so what I want you to do is prove this simply, right? And say that, okay, how do I prove that impossibility of consensus implies impossibility of leader election? Okay. And so this is a lot like the way that you do kind of proving something is NP hard or proving something is unsolvable. Hopefully you did a little bit of this in intro to algorithms, right? But what I'm saying is that, okay, well, if I have a solution to the leader election problem, then I can use this to solve consensus. Since I know I can't solve consensus, I know I can't solve the leader election problem. Right, exactly. Show if I can solve leader election, I can solve consensus. Right, so suppose I have a good, correct leader election algorithm. Right, how can I solve the consensus problem with that? Any ideas? Yeah, it's a reduction, exactly. Yep. So, yep. You can pick a leader, right? And then the leader makes the decision. So leader picks consensus value, right? And then the leader sends it to everyone. Remember, we have reliable messaging, right? So all correct processes are going to receive this decision and they're going to decide on that value. And I mean, it picks the consensus value. You just, in order to satisfy the validity, it just has to pick, there have to be some cases where it picks 0 and some cases where it picks 1, and then you've satisfied validity. And that's it. So that one's hopefully not so hard. Any questions about that? And remember, I told you there was some other problems. So maybe something to study would be other reductions. I think I told you 2 other problems. Okay, so at the end of class, I'll go over the topics, like what exactly is going to be on the quiz, but we'll finish up, or hopefully finish up Byzantine generals now, okay? All right, so back to the Byzantine generals problem. All right, so I just want to do a quick recap. The model, so this time now we're in a synchronous system, right? So we can execute an algorithm in rounds and we can detect when messages are missing. We have reliable messaging. So if a message is actually sent, it will be received. But we have what we call Byzantine failures. So not just crash failures, but a little bit more complex failure model. And so what a Byzantine failure is, in essence, is, any process that does not follow the specified algorithm. That's what a Byzantine failure is. And so that can be because we have some malicious actors. It could be hacked, and it could be either like a lone wolf kind of situation, right? One bad actor, or it could be collusion. It could be a bunch of processes working together. That's another way we can have Byzantine failures. But it could just be, not even malicious, it's just buggy, right? The code is not following the algorithm because it has bugs. Or also crash failures. So that's just not following the algorithm. When you crash, you have ceased to follow the algorithm. So these are all kinds of Byzantine failures, Byzantine behavior. All right. And in the problem, we had kind of in the Lamport story time version of the problem, we have a general commander general that wants to send an order to all of the lieutenants, right? And some of the lieutenants are loyal and some of them are traitors. The commander may be loyal, the commander may be a traitor, but we want, the loyal lieutenants to agree, right? And so this is the requirements for this problem. The first was the agreement property, that all loyal lieutenants obey the same order. Okay. And when I say obey the order, I mean, output or return the value, depending on the context, the algorithm that you're looking at. And then the second requirement was what we're calling the validity. And that is simply if the commander is loyal, then the loyal lieutenants are going to obey the commander's order. If the commander is not loyal, so the commander has Byzantine failures, it could be that it sent different orders to different lieutenants. It could be that didn't send any orders. It could be it sent, orders to some lieutenants and then died and didn't send orders to other lieutenants. So any of those behaviors, in that case, then we want the loyal lieutenants to reach agreement on something, right? They either have to all attack or all retreat. Okay? And we talked about a specific message model for the Lamport's results and algorithm that we studied last time. And this message model was called oral messages. And so you can think of this as if the generals are talking to each other kind of pairwise, passing information. And sometimes these are called non-authenticated messages. And so, these have some nice properties that come kind of from this idea of just, two people speaking to one another, is that the messages are not corrupted or garbled. So you can assume that the generals are, understanding each other, speaking the same language and able to hear well what the other one is saying. And the messages are not lost. I said it's reliable, right? So you can, if you're doing this oral message, like this person is talking to you, you get the message, or you just keep talking until you get the message. And then further, that the sender is known, right? So we can't have a process send a message and lie that some other process sent it. But there is the problem that a sender can lie about what it received, right? So it can lie about a message that it's relaying. Right, so it's not originating from itself, but it's saying, hey, the commander told me to attack, right? It can lie. The commander could have actually told it to retreat. Okay? And so under this particular model, we have the theorem that there's no solution for this problem. For this Byzantine general's problem. When what? How many traitors? How many traitors can we tolerate and still solve the problem? Yeah, we need fewer than a third, right? And so it was kind of written in this slightly less than obvious way, but when the number of processes n is less than 3 times m plus 1, where m is the number of traitors. Okay. And the key thing here is this is a theorem that applies to oral messages. Okay, so this is specific to this message model. All right, so do you think this is a good message model? Are there systems where you think this message model makes sense? Can you think of a system that uses this message model? Yeah, human speech and conversation. That's true, unless you can do that weird thing where you can tell that people are lying by looking at them. I don't know, maybe your project 2, I don't know, project 3, right? So if we're putting information out there, without considering any security on the information transmission, right? I mean, here we have the sender being known, but we can't stop a program from being malicious, right? So if the code is just relying on, one other program to be like, oh yeah, that's definitely what's written in the database. Oh yeah, no, that's definitely what the request was. Oh yeah, that anything where you're trusting a process to relay information on behalf of another process, that's going to be this message model, right? Okay. So then after that, we did Lamport's algorithm, which is a recursive algorithm, which is not the most straightforward to understand, and hopefully my executions gave you some idea of how it works, but it's complicated to hold in your head, right? The number recursive, the number of messages blows up pretty quickly. And so then today I was going to give you a proof of that algorithm. That I sat down looking at the proof, and I'm like, this is really long, and I don't know if anybody wants to sit here and watch me write a long proof all day, and I don't really want to sit here and write a long proof all day, so I am not going to do that. It's a good proof. It's well written. It's clear. You can certainly read it in the paper. I will not test you on the proof on the exam, but maybe I'll just give you one thing. So if we're trying to prove that a recursive algorithm is correct, what kind of proof would we do? Yep, induction. So it's an inductive proof. See, induction in the wild, right? So you can go and read this proof. I'm confident after us discussing the algorithm, you can understand it. And the beauty is like, okay, a recursive algorithm is really complicated to understand. Inductive proof of it is really easy. It's just long. So I am not going to write it. If there is some big demand and you want me to put together a video on it, I will. But I feel very confident that you can read this proof if you want to. So instead, I'm going to do a different algorithm that's a little bit more straightforward and will be the topic for the next project, which is very light on, a lot lighter on coding than all the other projects, just as a heads up. So if you're feeling the weight of the projects now, it will get easier. But this is the algorithm, and this is new for this year. So if those of you who are sort of relying on resources from previous years, no problem, but this is new, so I haven't taught this one before. Okay. All right, so for this one, we're going to now use a different message model. And this message model is, I guess, also certainly realistic, just takes a little more care, and we're going to talk about authenticated messages. Okay, or sometimes called signed messages. All right, so how many security experts or enthusiasts are there in the meeting right now? Anybody? One? Couple? All right, now, so not me, for sure not me. So I'm just going to talk about kind of the conceptual idea of authenticated messages, but please, like, I'll do this and then you can correct me for my silly speech. I mean, I think I have the gist of it, but hopefully this is not too horrifying for you to watch, right? Okay, so what we're going to talk about first is how do we sign a message? And so I'll talk about, I guess, in the most abstract and embarrassing sense, embarrassing for me, not you. We're going to talk about public key and private key, right? So every site is going to have, say, a public key, right? That's their identity. This is their public identity to the world, is published. So this can be shared, right? And then every site is also going to have kind of the corresponding counterpart to that, the private key. And this should be kept secret, so it's never shared. And these are generated together so that they have certain don't worry, I swear this is really not, it's really not that, don't worry. So these are coupled together, they're generated mathematically so that they have a special property, and that special property is what I'm going to illustrate to you with, basically stick figure level detail at this point in time. So whenever we want to send a message, so the sender is going to sign its message, right? So the sender is going to sign the message in a special way where you take the private key, that's the secret thing that's only known by the sender, and whatever the message contents are, right? And you feed this into a function, math happens, right? And then out comes a signature. This is as detailed as we're getting. Okay, so then the sender is going to send, so what gets sent is the message, the signature, the digital signature, right? And then, the public key, or this can be accessed in another way, it's fine, but the public key is public, right? So this is what gets sent. And then the recipient is going to get this. And it's going to be able to now verify that the contents of the message are as they were sent by the sender and signed by the sender. And so recipient gets the message, gets the signature, and it has the public key, right? And then these three things go into math, right? And then out comes a yes or no answer. Okay? This yes or no is saying, does this signature correspond to the sender and the message? Okay? And so that is it. That is all I'm going to go into in details on that. I mean, there are a couple kind of asides is that, things about this math is very special. One, that it's fast, right? So this is not us churning on a supercomputer for 4 days to do this signature, to do this testing. And also that you can't really forge it, right? You can't fake it. At least you can't fake it well with the absence of, say, quantum computers or something along those lines. Okay, so it's safe, secure, and it's fast. All right, security people, how'd they do? Shaking your head in horror. I mean, I know, the art is in the math. No comment, no comment. Yeah. You don't even need to take the crypto course. You could just take the final, you get an A, we're all done. Okay, so we're going to use these signatures now in this algorithm that we're going to work on, and we're going to just expand just a little bit on this. So what I'm going to use is a certain notation that if we have a message M, we're going to write something with these square brackets with I, and this is going to denote that I was, that message M was signed correctly by node I. It has a valid signature, and so if the recipient feeds, I's public key and the message and the signature into its math box, it will get that, yes, this is a valid thing sent by site I, okay? And then we can expand this, so because we're dealing with, it's not the same algorithm, but there is a notion of we need these sites to reach agreement, so they need to relay messages that they receive. They need to say, oh, the commander told me this, right? And so the way that they're going to do that is not through these oral messages, but they're going to take, say, a message M that's signed by I, and we could say maybe I is the commander, and then J is going to sign that as well before it sends it again, right? And so this just means kind of a shorthand for writing that there's this message M signed by I, and then that gets wrapped up in a message which gets signed by J, right? And I can make this list longer, so I could have M, I, J, K, right? A list of processes here. So as each one of them forwards the message or sends the message on, it's going to add its signature to this list. And the recipient can verify the whole chain of custody of this message. It can say that, okay, J forwarded this message correctly, I know what this message is, and then this message was originated at I, and this is I was definitely the sender, and M is definitely the contents, right? So this chain of signatures is like a secure chain of custody, and it can validate who sent the message and that it wasn't changed anywhere along the way. Okay. So this is a slightly more complicated messaging model to implement, but it gives us a big benefit when it comes to trying to do Byzantine agreement. All right. So the algorithm that I want to talk about is a paper that's posted on the website called Authentic Algorithms for Byzantine Agreement. Okay, and this is by Dolev and Strong. And so it'll be referred to as the Dolev-Strong algorithm from 1983. So a little bit, I think, 1982 was the Lamport paper. So obviously Lamport's paper made an impact and people followed up. Unlike other papers that I have presented, this one I don't think is an easy read. there are multiple algorithms presented in this paper, kind of all variations on a similar theme, but they're all presented basically as proofs of theorems. Like this problem can be solved in this amount of time, and then the proof is here's an algorithm, right? And it's readable, but it's not as accessible as I would say some other papers. So instead, I would recommend there's a draft textbook that I found that's actually quite good. And this is in chapter 3. The textbook is called Foundations of Distributed Consensus and Blockchain. It's by Professor Elaine Shih at Carnegie Mellon. And it's just it's like a draft book, and you can just download the PDF. Probably the whole book's good, but chapter 3 is good. I haven't read the whole book. Can loyal lieutenants crash and fail, or does only traitors lieutenants? So by crashing, that makes it a traitor. So any sort of failure, whether it's like a malicious behavior or just a crash, is considered a traitor. Okay. So this is, I'm going to present similar to what Professor Shih presents in this book. Anyways, it's a draft. It's free. You can download it. And the reason I'm doing this algorithm one is because it's a little easier, but it also is used in some blockchain implementations. And I'll do the last lecture. I'll talk about blockchain for those of you who are interested. But this is sort of the new-ish and still considered very popular way of doing a replicated log. And in the open world, it's used for Bitcoin, but it's also used for, at least considered and used for kind of supply chain tracking and, all of these things, if any sort of place where you want a secure way to track the transfer of goods. But I think a lot of times people, at least in the past, have just jumped on the blockchain bandwagon and said, yeah, we need blockchain, but really they just want a replicated log. Like they could just use Paxos, they'd be fine. And so what I'm hoping to give you through this course is some different options for replicated logs, at least through the sequence of projects that we're doing. And you can see the pros and cons of each. So this is the Byzantine agreement blockchain-esque replicated log. Okay. So we're going to use slightly different terminology just to line up with the textbook in case you choose to read it. So we're going to have a network of n and nodes, and so node is the word that we're using instead of general. And they're going to be numbered 1, 2, 3 up to n. And without loss of generality, we're going to say node 1 is the commander. And what they call this in both the paper and the textbook is the sender, so the one that's trying to transmit the order. We're going to say that B is the commander's order. And it's just a bit. This is why they use B. So it's going to be 0, which is retreat, or 1, which is attack. All right. And each side is going to store a set V sub I, which is the set of values that it's learned about throughout execution of this algorithm. So this is a set of values sort of called extracted, and that's a term from the algorithm. But extracted just means that they're past the signature validation. So I'll write that down. So if a site receives a message B and it has a list of signatures on it, because it's been relayed through a bunch of nodes. So let's just say it has J1, J2 up through JK. So it has these K signatures attached to it. If it gets this message and these are valid, like K distinct valid signatures, then that means that we can extract the value. That means that this message is, originated by J1 and not altered by any of the K minus 1 other nodes that relayed it. So when a site receives a message of this form, it's going to do the validation, the math, right, to check that all of these are valid. And then if it's valid, then it extracts that value and it sticks the value in its set VI. Okay? Okay, so now that's the notation for the algorithm, and now I'll give you the algorithm. And fortunately, it's very simple. A really strong algorithm. And so it's going to be done in rounds. And if there are M traders or M failures, we need M plus 1 rounds of this algorithm. Well, really, M plus 2, but you'll see. Okay, so we have round 0. That's the start. And this is where node 1 is going to send its value, right? Its bit, whatever its vote is, 0 or 1, and its signature, the signature of node 1. Now, of course, if node 1 is faulty and it fails to send, that's possible. And it also could send, a different bit to different other nodes, and that's fine. So it's going to send it to the all. So it doesn't have to send to itself, but sends to everybody else. Okay. And now for each round, a 1 through M plus 1. So I'm going to use R as my indexing variable. Each round, R equals 1 to M plus 1. At each node I, we're going to do the following. It's going to receive any messages that were sent to it in round R minus 1. Okay. And it's going to discard any messages that have invalid signatures, like the chain of signatures is not valid. Okay. And then so now for each of the ones left, it's going to be valid. So it's got the valid chain of signatures. And I'll write this as, so each valid message is going to be of the form, has a bit, B tilde, and then it has a list of signatures. And the first signature is from the commander, so from node 1. And then it's going to have some list up through R minus 1, right, up through the round in which it was sent. So those are the signatures, and they're distinct. Well, otherwise it wouldn't be valid, right? So this is what a good message looks like according to node I when it receives it. So when it receives this, it's going to check, have I received this bit before? So is B tilde not in my set VI? And if it's not, then it's going to add B tilde to its set VI. And then it's going to relay B tilde to everyone. So it's going to send that message B tilde with all the signatures that it got up through R minus 1. And it's going to add its own signature. All nodes, okay? So at the end, it's going to add its I signature. Okay? And then at the end of round m plus 1, that's when that's the algorithm's done. It has to decide what value to return, what order to obey. If there's only one thing in its set vi, its set of extracted values, so if the size of that set is 1, then it's going to return the bit that's in vi, right? Either the 0 or the 1, the attack or the retreat. Else, if vi doesn't have anything, or if vi has 2 things, it's going to return 0. Okay, that's the algorithm. Are there any questions on the code, my handwriting? How do we know M? So that, again, it's a good question. It's just like, I could have used little m here. It's just the number of traders that you can tolerate. So it's really an algorithm parameter. Yeah, you don't know, unfortunately. And if you set M too small, then and you have more traders, then you're out of luck. Yeah. Okay. All right, I'm going to scroll up. If anyone needs to see the code for longer, just give a chat yell. We can tell a message is invalid if the message received is not equal to applying a specific public key on a signature. Yeah. So in fact, when you're going to validate, you're going to kind of peel like the layers of the onion here. First, you're going to say like, is eyes like if someone received when I checks this message here, it's going to say, okay, well, is the message that's up to signature JR minus 2 validly signed by JR minus 1? And then is the message, that's up to JR minus 3 validly signed by R minus 2? And you're going to peel back the layers of the onion so you get back to the verify that this is exactly the message that was sent by the commander. So by doing this validation, you can check that nobody altered B tilde along this chain of forwards from 1 to R minus 1. Does that answer your question? Yeah. So, I mean, the problem we had, or the challenge we had with Lamport's algorithm is that like a trader lieutenant could say, oh, the commander told me attack. And, even though the commander said retreat, right? So you can't do that here, right? There's no way for a lieutenant to lie about the message that it received from the commander because it can only forward the commander's signed message. And it can't change the content of the message, otherwise the validation will fail. Okay? All right, so let's do just a few quick executions just to make sure this makes sense. So we'll do simple examples now first, which may seem silly, but we'll get to an interesting one soon enough. Oh, color. So we're going to have 4 sites. Now, there's no reason I don't need to have 4. This isn't the same as I had for Lamport's algorithm, but I'm just doing it this way. So we're going to say that the red site is the trader. So red equals trader. Okay. And so we're going to start with iteration r equals 0. And in this case, the commander is going to send messages to all of the other nodes. And I'm going to write attack and retreat here just for kind of simplicity, less numbers. So it's going to send attack assigned by itself. It's going to send the same message to all 3 nodes because it's loyal. Okay. And at this point in time, then these nodes, we don't care what 4 does. 4 is not to be trusted, right? But 2 and 3, they're going to add that, they're going to check the signature. They're going to say, okay, yeah, this is definitely sent by site 1. So I'm going to update my set VI, right? So V1 is going to become now attack, or a 1 value. Sorry, V1, V2. V3 is going to become an attack, right? So now they've extracted successfully that attack value. This is the first time they've received attack, so they put it in there. And now they're going to go to R, that was sort of R equals 1, right? So now they're going to go and they're going to do their sending. So this is where R equals 1 starts. So Lieutenant node 2 is going to send to 3 and 4. It's going to sign that message A and forward it on. So A, 1, 2, A, 1, 2. Similarly, a loyal Lieutenant 3 is going to send to 2 and 4. We'll send A, 1, 3, A, 1, 3. And now we have Lieutenant node 4 here. Now, node 4 is a traitor, but what can node 4 do? Like, what bad things could node 4 do here? What are the list of possible behaviors that it can do? What is a behavior that it can do? Cannot send any messages, right? So that it can definitely do that. It can follow the algorithm, but that's perhaps not interesting, right? Can it send retreat? That's the question. Can it say, hey, 2 and 3, the commander told me retreat? Right, it wouldn't be a valid message. Yes, so they do need to know each other's public keys ahead of time for this to work. Or, yeah, that's true. So it won't be a valid message. So it can't send, or can't send retreat 1, 4, right? I mean, it could send it, but it's not going to be valid. So it can't send a valid, right? A valid version of this. That's not going to happen, right? So either it follows the algorithm or it sends nothing. Okay, I have a magical math black box that's going to do the right math. It's magic. That's what all math that I don't understand is called, is magic. Fortunately, I understand a lot of math, but this one. All right, so it can't do this. We're going to assume we have good hash functions and good math and whatever we need. So kind of in this case, if it relays the attack, then it's not being a traitor, it's being a correct process. So let's just make it not send any messages because that's the most interesting thing we can do. Okay, so now we're going to look at, okay, so what happened? So at this point in time, V2, it received the message. So it received this message from process 3, but it already has an A in its set V2, so the set stays the same. And if there were any more steps to the algorithm, it wouldn't send any more messages. The algorithm is done. And similarly, V3 receives this attack message relayed by process 2. So their two sets, V2 and V3, remain the same. And this is the end of the algorithm. We're done. So we're going to return, they both are going to return A, and that's good. That's what we wanted, right? They both return the commander's order. Okay. Okay, so now let's just do kind of for symmetry, what happens if our commander is the traitor? And again, I'm doing this for now, m equals 1. So we start with our phase 0, r equals 0. We have one bad guy commander and our 3 loyal lieutenants. And in this case, the commander is going to send mixed messages. So we'll say it sends attack 1, attack 1, and retreat 1. And now in this case, all 3 of these are valid, right? They're all sent by site 1. Site 1 has the private key for site 1, so site 1 can, create a valid signature for all 3 of these messages. And so when these messages are received at sites 2, 3, and 4, they're going to pass the validation test. So then we get to round 1, and site 2 receives this message. It's going to update its list of extracted values to be A. Site 3 is going to do the same. And site 4 is going to put the retreat in its set of received messages. And it seems that now all 3 of them are going to relay what the commander told them. Right? So 2 is going to send to 3 and 4. It's going to say, I heard attack, and I'm adding my name to that. My signature, wrong way. That would be Byzantine behavior. Adding its signature. And 3 does the same thing. And 4 is now loyal, does the same thing. Okay. And then we can look at now at the end of this, what do our values look like here? So in r equals 2, we receive a new value. So site 2 is going to receive this. Sorry, I wrote an A there and nobody stopped me. Yes, thank you. These are retreats. So site 2 and 3 are going to receive these retreats. So back here, so now site 2 has both values in its set. So does site 3. And similarly, site 4 has received the attack from both sites 2 and site 3, but it only has to extract one of them. It's going to end up with an attack and retreat. And they're both going to apply that if test, and they say, okay, well, my VI has more than one element, so we're going to return retreat. All are going to return 0. So in this case, they all agree. Since the commander was a traitor, they can't try to agree on the commander's order, but they all agree on something, and everything is fine. Okay, so that's maybe not so interesting. So let's do maybe with 2 traitors, see something a little more interesting. So let's say now m equals 2. Now we have r equals 0. We'll make the commander a traitor, and we'll make site 4 a traitor. We have sites 2 and 3 are loyal. Now this is something that if we had oral messages, we couldn't solve this problem, right? The other ones we could have solved even if we had oral messages, but now we can't solve this with oral messages, okay? So in this case, let's suppose that the commander sends attack to site 1, sends attack, sorry, site 2, it sends attack to site 3, and it sends retreat to site 4. Now, of course, under this model, I'm assuming that 1 and 4 are not colluding. If they were colluding, it wouldn't even be necessary to send that message. And so then when we get to r equals 1, this, is everything going on? I'm getting all these RPI alerts. Anything okay? Okay. So they all update their sets, v2 and v3, to be the order that they receive from the commander. And I mean, it's not really relevant, but let's just say that v4 gets this retreat. Okay, now we go. This is the first time that v2 and v3 have extracted A, so they're going to send messages. So 2 is going to send the message to 3 and 4. And 3 is going to send the message to 2 and 4. And number 4 is the trader as well. And so 4 is going to only send a message to 2. And it has to send retreat because that's the only thing that 2 is going to, well, it doesn't have to, but the only way that 2 would possibly validate this is if it sent retreat. So it's going to send this R14 to 2, and it's not going to send anything to 3. Okay, so what now at the beginning of R equals 2, what does site 2's set of V look like? What's in there? Right, it has both, right? It has the A from the first time, and it has an R. And what does V3 look like? Right, just has an A. So if the algorithm stopped now, they would disagree, right? And so this is why if we have these 2 traders, we need to go one more round, right? When we only had 1 trader, we were done at this point in time, but if we have 2 traders, that's not enough, right? We need another round. And so what happens in the next round? Or I mean, what messages are sent in this round? So who sends a message next? Okay, so we don't know how many traders there are beforehand, so I guess I probably should have used little m. We just say that we're going to run our algorithm for some number of rounds, right? We're going to say our algorithm is going to run for 3 rounds. And that just means that if we have 2 or less traders, we will get the right answer at the end. So we don't have to know how many traders there are, but we can prove that if there are fewer traders, if there are less than m or less traders, and we run for m+1 rounds, then we're going to be correct. Great, yeah, sorry, that might be a little confusing. I should have used little m. Okay, so yeah, we're saying 2 is going to send to 3. I mean, it could also send to 4, but yeah, so we'll say 2. We don't really care about 4, and also it heard from 4, but the algorithm doesn't really say to restrict it. So it's going to send retreat 1, 4, 2, retreat 1, 4, 2, right? Does 3 send any messages? No? It's either no or yes. Those sometimes, yeah. Right. So if you look back at the code, I won't scroll back right now, but It's only going to send a message the first time it adds a new value to its set vi. If it doesn't have any new entries, it doesn't send any messages, right? So in this case, because v3 was at A here and then A in the previous round, it doesn't send any messages. Now 2, because it was at, A in this round and then it added an R, it sends messages. And we don't care what 4 does. 4 is not helpful, right? v3 doesn't send anything. Right? And then it does all the receives at the end, and now what happens, v3 got that retreat, right? So at the end of this, v2's set is still the same, they are, and then v3 now has a retreat. And so they're both going to return retreat. Right? So we need that one extra round on top of the number of potential traders in order to guarantee the correctness. Okay? Questions about the algorithm execution? All right. So I'll try to sketch the proof. It's very well written in the textbook as well. So our theorem is that this algorithm solves the Byzantine generalist problem. In m+1 rounds, here I have a little m, if there are at most m traders. And so just remember, just like that previous theorem was from Lamport was for a system model, this is with signed messages, with authenticated messages. Okay. So the question was, what if P4 didn't send the R it received? Yes, then they would both return A. So if P4 didn't send anything, then they would still both agree. Just like nothing would happen in the last round. Okay. Other questions about the algorithm? Yes, only non-trader processes need to agree. Yes. These are both little m. So, I mean, I used big M in the algorithm, so I should, but like, think of this as, we have a number of rounds of the algorithm, and that's, we go up to m+1, right? As long as there are at most m of those as traders, we're fine, right? As long as big M is less than little m, we're good. In general, would a system know the number of traders? No, definitely not. I mean, if you knew you were hacked, right, you could probably deal with that another way rather than just running this algorithm. And you can't predict bugs and faults and things like that. So yeah, I mean, nothing is ever totally secure, but you kind of make a bet on how I guess, vulnerable your system is and how many sites you think could be either buggy or compromised, and you run the algorithm given that best estimate. Could this algorithm work when the total number of traders is equal to the number of sites? Gosh, that's a good quiz question. No, I won't use it, but so what's the rule? What if they're all traders? What makes the algorithm correct? Right, no one needs to agree, free for all, right? So yeah, they could be anything. We don't care what they do. If they're all traders, they can just not output anything or output R or output A, it's fine. If all of them are traders, then any algorithm is correct, I guess. Although as long as yeah, it doesn't have to do anything. So, man, that was a good question. I'll have to remember that for next year. Does that make sense? I mean, you got to look at and this is, going back to kind of my favorite part about this topic, I guess, because I really like rules, right? But like, you got to look at what the properties are, and the properties don't say anything. Traders, we have no requirements on what traders do. Yeah, get played. That's my consulting gig. I'm going to implement this one. Big money, much bigger than academia. All right. So I don't want to write a long proof. This one is not long, but I do want to sketch it for you because it's straightforward, but it's always nice to see a little bit of formalism. At least I feel it's important, right? So we're going to just talk about the agreement property first, and then we'll talk about the validity. So what does agreement property say? As we just had this discussion. Agreement. What does agreement say? What's that property? No rules. Whoa.
All loyal lieutenants obey the same order.
Exactly. All loyal lieutenants obey the same order. No rules for traders. They can do whatever they want. No two processes decide, like all, oh, it doesn't matter. So not no two processes, but only the loyal ones. If you're hacked, like we can't make you not, be hacked, right? And output a correct value. We're just going to let you go. But we just need anyone who's not compromised to output the same value. Great. Yes. So we're going to talk about that, right? And so not divided into lemmas in the paper, but I think that in the textbook it's nicely divided. It's these two short lemmas, not short to write, but short to prove. So if by the end of some round R, I'm going to say correct, no, but some loyal lieutenant I has a value b tilde in its set bi, then every loyal lieutenant j will have b tilde in bj by the end of the next round. Okay. So if we look at the algorithm at any step in its execution at some round R in the execution, and we say, okay, I look at some site and it's loyal and it has a 0 or an attack or a retreat and it's set VI, then if I look in all the other loyal tenants around R+1, I'm guaranteed to see the same value. There might be other values, but I'm guaranteed to at least see that same value. And this is pretty straightforward, but we're going to say that b tilde, so I'll write the proof, was added to that set VI in round little t. And little t is going to be, by definition, it's going to be less than R, right? Which is going to be less than m+1, or strictly less, so it's, strictly less than m+1 because we're not done with the algorithm. Okay? Let's just say that's when it was added. This means that it passed all the rules of the algorithm. So it means that node I received a message that had all the valid signatures, right? And then it stuck its own signature onto it and it relayed it out. So it had received at this point in time the value b tilde in that round t that had the signatures. They're all valid, so it had these t distinct signatures, right? And they're all valid. And then it adds I and forwards it out. And these are all going to still be valid signatures, right? Because I is correct process. And we know that I hadn't already signed this message because if it had already signed this message, it meant it would have added b tilde to its set in an earlier round. And this means now that I is sending this out, then for sure, if any correct process hadn't already gotten a valid message with b tilde, this is the valid message with b tilde. So it's going to add this b tilde to its set when it receives it in round t+1. It says all loyal lieutenants extract b tilde in round t+1 if they have not already done so. Okay. Which is just a really long and fancy way of saying that, if a loyal lieutenant gets a value in some round, then, everybody is guaranteed to have it who's loyal by the next round. Okay. So now we have to kind of do the backwards part. That's just saying, like, what if we look at the last round and we see it in some loyal lieutenant's set VI, then is it definitely in all the other loyal lieutenants' sets? And that's lemma 2. Let me know if you need me to scroll down, up, whichever way you call it. Okay, so if some correct node I has b tilde in its set vi by the end of round m+1, then every correct node j has b tilde in their set vj by the end of round m+1. And sorry, I switched terminology. So correct node is loyal lieutenant. Does this prove that the cardinality of vi never needs to go above 2? I don't see why a process needs to keep relaying messages past the 2 different ones already broadcasts. Okay, I mean, that's a good question. Why would it keep processing? It doesn't, right? So its cardinality is 2. I mean, it's a set, right? So if there's only 0 and 1 in the world, then its cardinality is only going to ever be 2. But let's just scroll back for a second. If you look in the pseudocode, here, it is only going to send a message if when it sees that b tilde, it's not already in its set vi. So it is only going to send a new message if it's the first time it's seen the 0 or the 1. If it sees the 0 or 1 again, it doesn't have to do that again. So basically, your observation is correct, I guess. So does that make sense? Okay, so here's lemma 2, just saying that we're going to look now at the last round of this algorithm in n+1, and we're going to see if we say that we see some loyal lieutenant and it has a 1 in its set, then we need to make sure that every other loyal lieutenant also has a 1. And if it has a 0, we need to make sure every other lieutenant also has a 0. And so this encompasses the case if it has both 0 and 1, then they all both have 0 and 1, all the loyal lieutenants. So we have two cases to consider. We have to consider case 1, which is that this b tilde got added in a previous round. So right? So if that's the case, then what's my easy answer to why we know that all the other nodes have, correct nodes have the value in their VI? Am I losing you? All right, I'm losing you. Lemma 1, yes, thank you. This should follow directly from lemma 1, and if that's not obvious, it's just because I've been going on for too long. So let me write this down for you so you have it, and then we'll talk about it more later. Not today. So by lemma 1, then the result follows, right? Okay. And then case 2 is, now this is the first time in this round that node I gets this value. So I is added, or b tilde is added to vi in this round. And so this follows is that basically, in order for that to happen, this means that there had to be m+1 distinct signatures on that message, right? Right? And why is that important? Any idea why that's important? Right? In order for I to say that b tilde is a valid message, it has to check that there are m+1 distinct correct signatures. Well, so all other sites have had it. There's n sites, right? And n can be bigger than m, but at least one of these is not a traitor. At least one correct node in this set signed it, right? And that's the important thing, right? So at least one correct node received this message in a previous round and signed it and forwarded it. Right? Because there's only m traders, so at least one of those m+1 signatures has got to be from an honest, correct node. And so then, now we know at least one node got b tilde in its set at a previous round, so how do we know that now every correct node has to have it? Finish this proof for me. Lemma 1, again, right? This is, so by lemma 1, we're fine, right? This is a useful lemma. Right? And that's it. That's the proof. QED. Now this was agreement. This was just saying that if the commander is a traitor or not, we guarantee. I'm sorry. This was agreement. So what about validity? That means that if the commander is not a traitor and the commander signs its message and sends it out there, it's going to be correctly received by everyone in that R equals 1 round. So how do we know this algorithm satisfies validity? All right, so we can't forge it, right? If the commander said the value is attack, like we can't have anyone else lie, right? And so that means that the only value that's ever going to be anywhere in the system is the commander's value. No one else can introduce any more values. And since the commander is loyal, like that value got into all the other loyal lieutenants' sets right on the first round, and no one else can change it. So all correct, nodes are going to receive E1 in the first round, right? In round R equals 1. And no other values are going to be introduced. Or I guess like 0, whatever the opposite of B is, not B will never be introduced. So if we knew we had a loyal commander, we would not need to go through all this fuss, right? With loyal commander, it could just sign its value and send it out and be done with it. And so like a lot of the fuss in both of these algorithms is what do we do, how do we get around that if we don't know if the commander is loyal or not? All right, last question, message complexity. I'm going a little like the full time today, it's crazy. Message complexity. Big O notation. Yes, this algorithm solves it if there's a non-loyal commander or a loyal commander. Either way, solves in both. How many messages does each process send in the worst case? Somebody just asked this. Yeah, so it's going to be 2 messages per process, right? At most, 2 broadcasts per process. And when you broadcast, you send to everybody. So that's n-1. And so there's n-1 processes sending at most 2 n-1 messages. So message complexity here is order of n squared, which is definitely better than Lamport's algorithm, and I'll tell you that. But we have a stronger kind of security mechanism to work with. Okay, so just to finish up actually in time, quiz topics, exam topics. So we started off with leader election. Increased security results in decreased messages if you have authenticated messages. So it's just a completely different message model. Like if you're in a system where you can have authenticated messages, then you can you can tolerate a higher number of traders with a fewer number of messages. So this is where the system model is imposing the limitation. And both of these are kind of fundamental, like we can't do better, but it depends on the system model. Okay, so the leader election was what we started with, right? And we had 2 algorithms for this, the ring algorithm and the bully algorithm. Okay. And then we have FLP, which was, the theorem, kind of what it means and the proof. But um, that question that I went over earlier, that's as deep as it's going to get. I'm not saying that's superficial, but it's also kind of the length. I'm not going to ask you to recreate or rewrite large parts of a proof. And then we did the Byzantine agreement. And that'll be the formulation of the problem. So, how we step through kind of this consensus problem into this sort of broadcast problem in a way. And then we have Lamport's algorithm and no proof. And the Dolive-Strong algorithm. And I will also, based on kind of how things are going, I will not ask you about the proof, but I will ask you about the algorithm. Okay? Questions about topics? Like the coverage questions?
So what sort of questions would we be asked for like a leader election problem? Does this guarantee X or Y?
I mean, I think more along the lines of, my standard, if we slightly change something about the system model or the algorithm, does it still work kind of questions. So, I mean, and, we talked about, like, these are for, the bully algorithm is for a synchronous system model, right? So, or what are the assumptions on crash failures, those kinds of things.
That makes sense. Thank you.
Okay. All right. It relies on the magic of the math block being good enough to be too hard to solve in the time where the messages are relevant. Okay. Yes. I mean, that is true, right? This is only as true, as good as the scheme is for authenticating or making the signed messages. And to be clear, I did illustrate this kind of in the, albeit silly, superficial content, explanation of public key, private key signing. That's not part of the algorithm, right? The algorithm says, I need you to have a building block that gives me this message property of being able to sign messages. You don't need to use this scheme to do it. So, yes, if this scheme is flawed, that's going to break the security here. It's going to break the safety of this algorithm. But it's, kind of the contract is you give me a messaging model that satisfies these properties and my algorithm will work.